Let's begin by correcting a small issue from the previous video. We had a coordinate transformation from t and x to v and x, and v is related to t and x in this way, and so therefore it must be that ct is equal to v minus x, and that c dt is dv minus dx. I think we had the opposite sign here. It doesn't really matter once you put it into the line element, you end up with the same thing. So there we showed how to go from t and x coordinates to v and x coordinates, and that just did something to the light cone. It sort of stretched the light cone. We want to do the same thing now for t and r to v and r, to stretch the light cone, which in these coordinates closes up at the location of interest to us, r equals 2gm over c squared. So in this case, we're talking about v equals ct plus, similar to this, the distance in space between 2 points, which in the radial direction involves the integral of the dr over 1 minus 2gm over rc squared, which ends up giving r plus 2 when we integrate that. It's kind of silly to integrate it because we'll end up at the same place when we do the dr. Log of c squared r over 2gm minus 1. So this is the proper distance in the direction of the radial coordinate. Let's see. So now we have, similar to what we did there, we want to solve for ct, which becomes v minus this stuff, minus r minus 2gm over c squared, natural log of c squared r over 2gm minus 1. And so c dt, right, which we're going to square this when we put it into the line element to get the line element in terms of VR coordinates. C dt becomes dv minus dr minus 2gm over c squared. Well, let's just do it, but it's kind of silly because we should recognize that it's just going to end up at dr over 1 minus 2gm over c squared r. So let's go through the derivatives anyway. C squared over 2gm over c squared r over 2gm minus 1 times dr, which is dv minus dr plus dr over 1 minus c squared r over 2gm, which is, let's put a minus sign here and flip these two, and so we'll end up at minus sign. Then we'll pull out a gm here. Well, let's just go through this. The dv, here we have plus dr times 1 over 1 minus c squared r over 2gm minus 1, which gives us dv plus dr times 1 over 2gm over c squared r minus 1, which gives us dv minus dr times 1 over 1 minus 2gm over c squared r, which is, of course, where we started. So now we want to square this and put it into the line element. Okay, so the line element is ds squared equals minus c squared. That's 1 minus 2 gm over c squared r in dt squared. Right, so we want c squared dt squared. Then we have the plus dr squared, 1 minus 2 gm over c squared r, plus the angular part. So usually it's referred to as that, the theta squared plus the r squared sine squared theta. The phi squared is this object here. So this becomes, in these coordinates, we're replacing c dt squared with what we just found, and we end up at minus 1 minus 2 gm over c squared r dv squared plus 2 dv dr plus r squared d omega squared, which is very familiar to us from what we did in flat space time. And now we'll consider what we did there, which is light, or rather radial light, right? Light traveling in the radial direction only. And so the line element reads 0 equals minus 1 minus 2 gm over c squared r dv squared plus 2 dv dr, and therefore we'll divide by dr squared, and so this becomes 1 minus 2 gm over c squared r dv by dr squared plus 2 dv by dr. And so our solutions are dv by dr itself equals to 0. And sorry, the equations are dv by dr equals 0, which has a solution v equals constant, which similar to what we saw before when we did this transformation, and dv by dr equals 2 over 1 minus 2 gm over c squared r. So this the derivative of v in r is changing with r in this way. And so we can look at a VR diagram and see light, right? So we can plot this constant v. These are lines of constant v. Right, so this represents light traveling to lower radial values. And then we have dv by dr given by this, where the slope is changing as r goes to large values. This goes to 0 and this goes to 2, right? So as we saw before, and so that slope is changing as we're approaching smaller and smaller values of r. As r is approaching 2 gm over c squared, this is getting, the slope is getting larger. So we have a varying slope. How to do this? Something like this. Something like that. And so when we play around with the light cones, it looks something like that. We've opened them up. but at r equals 2gm over c squared, this is 1 minus 1 is 0, so 2 divided by 0. So we are at infinity. So this is 2gm over c squared. And so the light cone is doing that. And because v equals constant represents light going to the left, we can kind of make contact on a TR diagram. If we sort of tilt, I've seen tilted v, where we do VR, but we sort of tilt, we have oblique axes. And so we put these lines like this, where on a TR diagram they would be 45-degree lines, and then the other ones would be like this, is changing slope or something like that. Well, I have to be a little more careful here, but something like that. The point is that we now have some sense of what these light cones are doing at this location 2gm over c squared. We basically see that the light cone has tipped over. It's not closing in on itself anymore, so we've succeeded in opening up the light cone. But what we see is that it's no longer possible to go to R values that are greater than this value once you cross this line. Okay, and so this is really the first place where we see some evidence that this is a special kind of location that ultimately we call the event horizon of a black hole.